Well, we're going to start on what you're going to need for the mastery test. The mastery test on the syllabus, it says that it's a week from tonight. It's going to be, we're going to push back 2 weeks from tonight. It's going to be the mastery test. Okay? So what we're going to start working on today is the stuff that's what's called the derivative mastery test in the second half of class today. But I want to just bridge the gap one more time. And here's an example that just kind of encompasses a lot of ideas of this reverse process, right? You know what? In the reverse process, you know I got my sheet today. In the reverse process, you know. Where's Tyler? Randette. In the reverse process, you know what, Tyler? What's that? Oh, it's what we've been doing for 2 weeks. Okay, Adam. Where's Adam? In the reverse process that we're working on, you know how much, what?
You know how much you have and you want to know how fast it's changing.
That's right. You know how much of it you have and you want to know how fast it's changing. Okay? So that's what we're on right now. So here's hopefully an easy task. Here's an approximate that we're showing with this kind of this pink secant line. Connecting on this function g to points 1, 4, and 4, 2. What is the approximate rate of change represented by this pink secant line? Go, you got 20 seconds. What's the approximate rate of change represented by that pink secant line? Figure it out. Okay, where's Kaylee? Capablanca. Kaylee, can you tell me what did you get for the approximate rate of change?
I did 2 minus 4 over 4 minus 2 was negative 0.66.
Okay, 2 minus 4 over 4 minus 1. So you got negative 2/3?
Yes.
Negative 2/3. So here, and what's our h value? Our h value is 3. So for this h value of 3, we got a rate of change at 1 of negative 2/3. Good approximation or bad approximation? Look how much daylight there is between the two, right? So if we were to zoom in, come on. If we were to zoom in on here, so we see that the actual rate of change is different, quite a bit different than what the pink line shows. So how can we get a better approximation at 1,4? How can we get a better approximation at 1,4? Where is Sterling? Zubel. Sterling, you here? Yeah. How can we get a better approximation at the point 1,4 for the rate of change? How do I get a better approximation for the rate of change at x equals 1 than the one we just calculated according to the pink line?
Use a smaller delta.
Yep, smaller h. Yeah, exactly. Smaller delta x or smaller h. Okay, so go. So identify what is h and find the new rate of change for those 2 points at x equals 1. What is h? And what's the new rate of change? Okay, where's Desiree? Desiree. Is Desiree here? No? How about Coles, Weber? Coles. No Coles? Yeah. So what's H now? Zero. Yeah, Cole. Who is Coles? You just answer. Awesome. Okay. And then what is H? 0.05. And did you get a number for the rate of change? Negative. Okay. So negative. I got one negative 1.31. I think we're close enough. Okay. So while we're here, let's also do the same thing down here at 4.2. I've got this 0.42. So find the rate of change down here for x equals 4. Okay, for x equals 4, I gave you a second point on the curve. Go. Okay, you should get negative 0.33. Someone get that? Okay. Are we okay if you got negative 0.34 and I got negative 0.33? Are we cool? All right. Hopefully you got the picture by now that that's not the kind of thing we're interested in this class. Making sure that the hundredths place is correct. Hopefully you've got that theme, okay? But that's not what we're about, okay? All right, cool. So that second rate, that number, negative 0.33, what does that mean? Yes, it is the approximate rate of change at the moment x equals 4. It is an approximate rate of change at the moment x equals 4. But what does that number mean, negative 0.33? Tell the person next to you. We should have it by now, hopefully. What's that? You need to leave the class? You need to step out of the class? Oh, okay. Just about to regroup. Let's talk after class, okay? Okay, where is Emily? Emily Armstrong. Emily here. How'd you do? So what's the meaning of the negative 0.33 in this context?
When x equals 4,
Okay.
the change in y, the change in y is negative 0.33 times y,
Okay, perfect except for one little detail. So that's perfect. When x equals 4, the change in y will be negative 0.33 times the change in x. For a small delta x, right? For a small change in x, okay? For a small, if the change in x is too big, then that won't be true. So for a small change in x. Okay, excellent. I wrote it this way. Given a small change in x near 4, y will change negative 0.33 times as much as that change in x. That's the way I phrased it. It's not, what she said was also well said. Okay, so how would you like to do this for every x value, say from 0 to 5? In order to get to know how the quantity, the rate of change of the quantity at every value from 0 to 5. How would you like to go through this for every x value from 0 to 5? No, we wouldn't, right? This is very tedious. We spent all that time and we only got 2 rates of change at x equals 1 and x equals 4. So thus, all this work we've done in the last week to build what? A rate of change function, right? And so the rate of change function, so this particular function is 12, this original black curve I gave you is 12 over x plus 2, some amount function. Now we have the ability to generate a rate of change function from this 12 over x plus 2 that can very quickly give us every rate of change, say from 0 to 5 or 0 to 10, whatever we want, instead of having to do this for every x value that we want the rate of change at. So that's what we've been doing the last week, developing a way to efficiently be able to find every rate of change. That's called a rate of change function. Okay? So let's do that for this one. So if g of x is 12 over x plus 2, let's just, so what is before we get to the rule, can you write the general form of the rate of change function? That's how we're always going to start. We're always going to start with our general form of the rate of change function, say for a function named g. What will the general form of the rate of change function for a function named g be? Julie Alvarez, can you tell me what the general form of the rate of change function for g is? Just like on your quiz.
G is x plus h minus g of x.
Good. This is the rate of change function for a function named g. Now, we have a particular rule for g. So we can apply the rule, like you did on your quiz. So now I want you to apply the rule to the general rate of change function. So if g of x is 12 over x plus 2, then what does that quotient become? What does that quotient become? Let's see where's Gunnar? Gunnar, you're up. Can you do that? Can you rewrite that general form rate of change function now applying the rule of g?
Is it 12 over x plus 2? 12 over x plus 2 plus h.
Okay.
Minus 12 over x plus 2 over h.
Yep. That's it. You switch the 2 and the h, but that's okay. Yeah. 12 over, so instead of x, we 12 over x plus h plus 2 minus 12 over x plus 2 all over h. And so what is our goal? Now our goal is to use algebra to get this into a useful form. And we're going to let h be really, really small. We want to get this into a useful form so we can just plug in values of x and it'll give us rates of change rather than doing all that work that we did for just those 2 points last time. So we got this numerator. How are we going to make progress on that numerator? We need a common denominator, right? We're subtracting fractions. The common denominator in this case is just going to be the product of the 2 denominators. So our common denominator is the product of the 2. That means the first numerator is going to be 12 times x plus 2. The second numerator is going to be 12 times x plus h plus 2 after we subtract the fractions. So common denominator, and then we got to adjust the numerators, and then we subtract. Now what? We can simplify that the numerator of the numerators. Okay, what we're going to see is that you got a 12x and a negative 12x. You see that? There's a 12x and a negative 12x. That's going to go away. And then what else? 12 times 2 and a negative 12 times 2. Those are going to go away. So all that's going to be left is what? Negative 12h. Do you see that center term on the second? That center term on the second product there. Negative 12h is all that's going to be left. Should be negative. Oh, if I remember right, there's several typos on this slide. So we'll just catch them as they come. So that's negative 12h over x plus h plus 2 over x plus 2. And what can we do now? I've got an h divided by h. They go away. So we could multiply out the denominator, but that doesn't really help us with anything. So we kind of, in terms of simplifying it, there's really nothing more to do to simplify it. So then we ask, so is this approximate rate of change or exact rate of change? Depends on h. So we want it to be, if we want exact rate of change, we let h be essentially 0. We can't let h be 0 because then we won't have any change. So we make h really, really small, right? Small enough so we can't tell the difference. So for h, essentially 0.
There shouldn't be a negative on
Yep, probably. I told you there was typos on this page. Is that right? Okay, so what did we just find? So now is this exact or approximate rate of change? This is exact. So this is our exact rate of change function. We'll still call it r sub g. That might be the next. Yeah. So our exact rate of change function is negative 12 or x plus 12. And so remember for 1, when we did our good approximation, we got negative 1.311. So I want you to find the rate of change at 1 exactly now. Find the rate of change at x equals 1 exactly. And so where's Brady Lorenz? Brady, how would you get now? How could you find the exact rate of change at 1 instead of finding 2 points and calculating delta y over delta x? What could you do now to get the exact rate of change at x equals 1? Yeah, right. We just found the closed form. So you just plug it. That's the beauty of closed form. You just plug stuff in and it chugs stuff out. Instead of having to do all the process, closed form is about rapid fire outputs. So you just do RG of 1. Anyone do it? What do you get? Oh, and our 4. So and 4 was negative 0.33. Here. Okay, so when you actually put in RG of 1, we calculated it as negative 1.33. What is it? 33333? Yeah. Okay, so our approximation was decent. It was decent, but it still had, a significant error to it. Good approximation, still with error. Now this is exact based on the algebra, letting h be really small. This is now exact rate of change at 1. What about at 4? Is that negative 0.3333? Or negative 1/3? Same thing. Again, we got a really good approximation, but the closed form rate function gives us the exact value, and now it gives us any exact value. You want the rate at 5? You just plug it into that. You want the rate at 2, 2.7, 5.9? Rapid fire results. That's the beauty of closed form. So this process, this algebraic process of applying the rule to the general rate of change function does a lot of work for us, and then it gives us every single rate at every single point very quickly. Okay, does that help tie some things together? Does that help? Anybody have a question? Okay, so let's regroup. Here's where we are. You know how much of a quantity you have at every moment. You want to know how fast that quantity changes at every moment. We also want a closed form expression for the rate of change. We just saw how powerful that is, right? We can get rates of change really, really fast. Closed forms expressions give us lots of results quickly. Okay, and this we got this from that sliding h interval approach. We got that rate of change function that can give us these closed forms. That was from our second approach at the reverse process using the sliding h interval. Okay, so here's our rate of change function. So we talked about how much of a quantity you have at every moment. You want to know how fast it's changing at every moment. So where in this is that you know how much of a quantity you have at every moment. Where in this expression is the aspect of you know how much of a quantity you have at every moment. Let's see. Where's Changwei? Run. So where in that expression do you see represented you know how much you have of a quantity at every moment? What about this is that? What is it? Yeah, so in the reverse process, we start by knowing how much of a quantity we have. So where is that seen in this expression? Where do we know how much of a quantity we have? Yeah, so yeah, right. You know, so f of x, that's our quantity function. That's either our amount function or accumulation function. So and then that's also f of x plus h, right? So f of x plus h or f of x, okay? And then we want to know how fast the quantity is changing. Where do we see that? Where is Camelia Tybowski? Where in this? So it says you want to know how fast the quantity changes at every moment. Where do we see that in this expression, in this definition? You want to know how fast it changes. R of f of x. That's what the whole fraction does. Good. So you know how much you have. That's the f of x. You want to know how fast it's changing. Well, that's what this whole thing calculates. And that's r of f of x. Good. And so what do we, this is our rate of change function. It's the rate of change of the function f with respect to its input x. That's what we say. It's the rate of change of the function f with respect to its input x. Okay, and so we saw, so with algebra and letting h be very, very small, the rate of change function can give us closed form exact rate. And that's what we want. Okay, so generalizing this process for different situations leads to these rules, rate of change rules or shortcuts. That's what we're going to start working on, and it's about these rules or shortcuts, which the mastery test is about. Okay. So, we're going to get into these a lot of memorization and working a lot of algebra, but we never want to lose sight of the meaning of rate of change, and so that will be our job, TAs and myself, to keep giving you little tasks in this process that keep us thinking about the meaning of rate of change. Okay, so that's kind of an overview of where we're at. We're moving on to the rules. So the first rule is for constant functions. Constant functions. If an accumulation function never accumulates any changes in its value, it's a constant function. What is its rate of change? What is its rate of change? The accumulation function never accumulates anything. Never changes in its value. What's the rate of change? Zero. Okay, so we want to show it mathematically. So if you have a function f of x, and we want to show that the rate of change is 0, how are we going to start? How are we going to start? We've got a function f of x. What are we going to start with? Where is Braden? Silcott. Good. We're going to start with the rate of change function. It's what we can rely on. It's what we know. Okay. So we have this function f of x equals c. It's a constant function. We're going to start with the rate function, right? This is true. This is what we trust. We rely on this. We know this is right. Okay. So what does the rule of this function say to do? So given a value of input, what does the rule say to do for this function? Given an input, the rule says do what? So we have some input, then what does the rule tell us to do to get the corresponding output? What's that? What do we do with the input to get the output? This is important. This is going to allow us to apply the rule. Yeah, tell me.
It always equals c. So you don't do anything to it. It's just the value of c.
Good. No matter what input we put in, it doesn't matter what you plug into this function. The output is c. So when we put in x plus h, what are we going to get? C. When you put in x, what are you going to get? C. Okay? So, therefore, what's the rate of change? C minus C over H. 0. And that's what we said. If a function doesn't accumulate any changes in its value, the rate of change is 0. So this is the mathematical proof of that using our trusted form of the rate of change function. Any questions? Okay. We've got a rule. If you've got a constant function, the rate of change is 0. Okay, here's a new rule. This is what we're going to call the constant multiple rule. This first screen is just kind of the idea of it. This is the idea of it. If at every moment in time John has traveled 5 times as far as Mary, what can we conclude about John's speed relative to Mary's speed? Is it 5 times as fast? Yeah, of course. If John goes 5 times as far as Mary for any time, then he must be going 5 times as fast as her. Okay, so that's the idea of the constant multiple rule. That if you have a function, so let's just kind of define these here. John's total distance after x hours is f. Mary's total distance is g. So what does this say? This says that the distance that John travels is 5 times the distance that Mary travels. That was the given information, right? That was given. And what is our conclusion? We concluded that John's speed is 5 times as much as Mary's speed. So how could we write that mathematically? How could we write that mathematically with what we're doing? Where is Keen? Miller? So now, how would you write, using the notation we have, that John's speed is 5 times Mary's speed? So speed, a hint, speed is the rate of change of distance. Speed is the rate of change of distance. Yeah, he wants to go.
So you start with the accumulation function.
Well, no, we just want to write the result right now.
Just for the results,
Yeah.
you can find the rate of change.
So how would we express mathematically that John's speed is 5 times Mary's speed? That's all I want to do. Just express it mathematically.
Just the speed, just that.
Philip, you want? Yeah. What's that? What?
5 times first begins to be 5x.
The speed. So the x is the speed. So the f of x is the distance. What is the speed? Yeah. Go ahead. Right. Speed is rate of change of distance. So this now expresses that John's rate of change of distance or speed is 5 times Mary's rate of change of distance or her speed. Now this is not a proof. This is just common sense and then expressing it mathematically. That's all this is. We haven't proved anything. Okay. Okay, and so then just some semantics. So the rate of change of f with respect to x is 5 times the rate of change of g with respect to x. That's what that means right there. That's how we say that. Okay, so now we want to prove it. So we're going to start, this is our given. I'm not sure. This is what we want to show. So this is our given. We know this to be true. And this is what we're expecting. This is kind of what we want to show or to prove. So how do we do it? Maybe for time's sake, this is a good one for recitation. How about we'll just go on? This will be a good one for recitation for them to do this one. Okay? So the proof of this is going to be the same as the proof of all the others that we're doing. Okay? But it's going to be one for you. Okay? It's going to be one for you. So we're going to move on. But this is the conclusion, that if you have a constant multiple of one function, then the rate of change is the constant multiple of the rate of change. That's the second rule. So if you have a function that consists of a constant multiple of another function, then the rate of change of that function is the same constant multiple times the rate of change. So it's kind of like that constant multiple just kind of comes along for the ride. So when you look to the rate of change of f, it's just going to be the rate of change of g holding on to the constant. Okay? That is the rule. Now we didn't prove it. Again, we'll leave that for you guys. Okay, so we got two rules. We got a constant function and a constant times a function. So what's the rate of change of a constant function? What's the rate of change? 0. What's the rate of change of a constant times a function? The constant times the rate of change of that function, right? So if you have a constant times a function, the rate of change of that is the constant times the rate of change. Okay, 2 rules down. All right, so the next rule we're going to do is for a function of the form x to the n, a monomial, x to the n. So in order to do this, to show this, we're going to have to look at a little reminder here of some algebra. So x plus h squared, remember, has a middle term. X plus h cubed ends up having 2 middle terms. And so as that power increases, you get more and more middle terms. You get more and more middle terms. And what happens? We always have, so if it's x plus h to the 4th, we always start with x to the 4th, and we end with h to the 4th. And then in each term, as we go from term to term, the power of x goes down by 1, and the power of h goes up by 1. So this first one we get is an x cubed with a single h. The next one will be x squared and h squared. And then the next one is x to the first h cubed, and then finally x to the 0, or no x's, and then h to the 4th. So then, so that's the same pattern you have for generically any power n. You're going to start at x to the n, and then as you march down from term to term, the power of x goes down by 1, and the power of h goes up by 1, until you get to the end where you have no more x, and then you have h to the n as the last term. So that's the pattern for these. This is called the binomial expansion. So that's as much as we need to know about it for our purposes. For our purposes, we just need to know it starts with x to the n, it ends with h to the n, and then it's just each term, the power of x goes down by 1, and the power of h goes up by 1. So that's basically what we need to know. Yeah? The power, that's what, the big picture of what we're doing is the power rule. Not this. This is the power rule. But we're working on the power rule right now. But that's called the binomial expansion. Okay. So we need that in order to find a rule for a function x to the n. Okay. So here we go. So I want you to write out. So we've f of x equals x to the n. N could be any counting number, starting at 1, 2, 3, any counting number. Okay? We want to know, what is the rate of change of f with respect to x? What is the rate of change of f with respect to x? So I want everyone to write down the first step. What's the first step if we want to find a general rule for the rate of change of f with respect to x? Write down the first step. Go. Just the first step. Okay, where's Noel? Laura. Noel, Laura. Yes. You made my day. What is it? Yes. Right. It's always that to start. This is our trusted form for the rate of change. So we've been working on for 2 weeks. The rate of change of f with respect to x is f of x plus h minus f of x over h. Change in y over change in x for 2 points. Let h be small. You get the exact rate of change. Okay, so now we want to apply the rule for the particular function we want. So how do we apply the rule x to the n to this? Where is Brianna Gonzalez? X plus h to the n minus x to the n over h. You guys are on it today. The best question answering day ever. Where's my evaluator? I need an evaluator today. All right, so x plus h to the n minus x to the n over h. That's it. Okay, but now on the last page, we just said what x plus h to the n is. Remember, we did the binomial expansion. So we're going to rewrite that. Wait, no. Like I said, listen. All you need to know is the first term is what? X to the n. The last term is, and what happens in between? Powers of x go down 1 each term. Powers of h go up 1 each term. That's all you need to know. This is not a scary monster. Okay? That's x plus h to the n, and then minus x to the n all over h. Okay, what do you see? What can we do in that numerator? We've seen it before. Notice, positive x to the n and minus x to the n. Bye-bye. Okay, so that's what's left. It's just all the remaining terms in the binomial expansion, starting from the second to the n. What's true about every one of those terms? They have an h. So we can factor out the h. So again, all I'm doing is pulling a single h out of all those. And then h over h is 1. And so then what we're left with is everything in that so the h divided by h goes, and so now what's here is just this parentheses rewritten. Okay, so what is that expression? That is the rate of change function for x to the n. Approximate or exact, depending on the size of h. If h is not small, we get approximate rate of change. If h is very, very small, we get exact rate of change. Well, look what happens when h is very, very small. What happens to this first term when h is very, very small? Nothing. It doesn't care about h. It doesn't have to do with h, right? H can do whatever it wants. It's n x to the n minus 1. What about this when h gets really, really, really small? 0. There's an h. But what did we say? Every term has more and more h's. So all of these are going to go to 0. So we're left with, for the exact rate of change, n x to the n minus 1 when h is really small. When h is really small. What did we just find? We found the exact rate of change function when your function is of the form x to the n. And the exact rate of, in closed form. The closed form rate of change function is n x to the n minus 1. Okay, so therefore, when f of x is x to the n, the exact rate of change function is n x to the n minus 1. Okay, we got 3 rules. First rule is, if the function is constant, the rate of change is 0. If the function is a constant times another function, the rate of change is the constant times the rate of change. And if the function is x to the n, the rate of change function is nx to the n minus 1. And we get all those by starting with our trusted rate of change function, f of x plus h minus f of x over h. And doing the math. We just do the algebra correctly, it gives us this closed form. Okay, and so this is the power rule. So that's your question, Kurt. So now that we've finished and we got the rate of change function, this is what we'll call the power rule. The power rule. So we got the constant rule, the constant multiple rule, and the power rule. Okay. The rate of change of a function that is a sum of functions. So I've got this function k, and it's the sum of 2 other functions, f and g. What is the rate of change of k? So let's just conjecture, before we prove it, let's just conjecture. What do you think the rate of change of k might be if it's the sum of 2 other functions? As a conjecture. What would you hope for? What would be the best possible result? That the rate of change of k would equal to?
0.
Well, yeah, that would be nice. What's that? The sum of the rate of changes, right? So the nice result that we would hope for would be the rate of change of k is equal to the rate of change of f plus the rate of change of g. It'd be like falling out of bed, right? It's like this is what we would hope for and be natural. Okay. Can you prove it? Go. Can you prove it? You're going to do it all now, at just the first step. See if you can do it all. Now, when you apply the rate of change function in the first step, it's to k, right? So we're interested in the rate of change of k. That's how you're going to start. You're going to write the rate of change function for k, and then you're going to work on that. Okay, so where is Jesse Hill? Where's Jesse? How do I apply the general form rate of change function if the function is k? Can you tell me what the rate of change of k would be? What's that? You don't know. Okay, how about Chongwei, Ron? Twice in the same day. What is the rate of change function for the function k? K for the function k. You got it, but it's not the function f, it's the function k. So it's not f of x plus h, it would be Good. Good. That's it. That's how we start. Okay, so now the question is, what is k of x plus h? If k of x is f of x plus g of x, what's k of x plus h? Where is Connor Fox? Connor. Is Connor here? Okay, what about Haley Schumann? Haley, if k of x is f of x plus g of x, then what's k of x plus h? Okay, is it f? It's not f of x plus g of x plus h. What would it be? Yeah. That's right. K of x plus h is going to be f of x plus h plus g of x plus h. All right? Minus k of x, well, we know what that is. F of x plus g of x. So this is what you get for the rate of change of k. This is what you get for the rate of change of k. Do you see it? We're using the definition of k here to expand k of x plus h. If k of x is the function f plus g evaluated at x, then k of x plus h is going to be f plus g evaluated at k plus h. And then this is simply minus k of x, which is f of x plus g of x. Okay, now we're just going to change the order in the numerator. I'm just going to group the f of x plus h with the minus f of x, and the g of x plus h with the minus g of x. And then I'm going to split it up into 2. So it's like when you add fractions, you have a common denominator. So it's like I'm going backwards and I'm pulling them apart into 2 fractions. So where's Brandon? Zavala. Brandon, do you recognize this right here? So now I've got this first fraction right here. Do you recognize what that is? What is that? Not sure. Yeah. Isn't that the rate function for f? That's exactly the rate function for f. And what's this? The rate function for g. Did we get what we wanted? Exactly what we hoped for, right? You use the rate of change function applied to k. You apply the rule for k, which is the sum of the functions. You just rearrange things. And when you rearrange things, you get that the rate of change of k is the rate of change of f plus the rate of change of g. 4 rules now. We got 4 rules. Here are the 4 rules we have. If the function is of the form x to the n, the closed form rate of change function is n x to the n minus 1. If the function is a constant function, the rate of change is 0. Hector's got that one down. If f is cg to the x, then the rate of change of f is c times the rate of change of g. We did not prove that one. That's a good exercise for you. And then, or for recitation, if k is f plus g, then the rate of change of k is rate of change of f plus rate of change of g. Okay, so here's a polynomial. It's got all the rules mixed up into one. So here's one function that we're about to apply all 4 rules to do this. So what we're going to ask is first, what is the overall structure of this function? Is the overall structure that it's something to a power? Is the overall structure that it's a constant? Is the overall structure that it's a constant times another function? Or is the overall structure that it's the sum of things? The overall structure, 1, 2, 3, or 4? Well, I heard lots of answers. What's the overall structure? Is it 1, 2, 3, or 4? Well, but in the biggest sense, the big picture of it, the structure of the whole function is one of those 4. It's 4. That function is, in its biggest sense, in the biggest sense of it, the big picture, it's the sum of 4 things. So we're going to apply that rule first. To get the rate of change of p, we're going to apply that rule first, and we're going to say the rate of change of p is going to be what? It's going to be the rate of change of x to the 11th minus the rate of change of 5x to the 4th plus the rate of change of 10x cubed plus the rate of change of 9. So they're all separate. So now this one, is this going to be an application of rule 1, 2, 3, or 4? 1. It's exactly like 1. It's something to a power. So what if it's x to the 11th? Then our power rule tells us that the rate of change is 11. So the n value, x to the 10th. 1 less. Okay, the power becomes the coefficient. The new power is 1 less. Okay, now this one, 5x to the 4th. The general structure of that is that rule 1, 2, 3, or 4. 5x to the fourth. 1, 2, 3, or 4. It's not 1 because it's 5x to the fourth. It's 3. It's a constant 5 times another function. And what does that rule tell us to do? It tells us to hold on to the constant and take the rate of change of the function. So it's going to be 5 times the rate of change of x to the fourth, which is 4x cubed. So I just applied 2 rules at once there. I applied the constant multiple rule and the power rule in the same step. Same thing with this. This is constant multiple rule. Rate of change is the constant times the rate of change. I know we're a little bit over. Just almost done. Last term. Rate of change of 9x. Is it rule 1, 2, 3, or 4? 2. Rate of change is? 0. So we just wrote the rate of change function for that polynomial. I'll stick around if you've got questions.